So we are continuing our discussion about the ion exchange membrane applications. So we have talked about the importance of these parameters such as electrical charge, resistance, density, selectivity, and transport rate, and stability issues. So we will go through one by one. And first of all, what about the electrical charges? If the membrane has the cations, then of course we call it as AN, ion exchange membrane, because anion will be gone. Then the pH will be different from the neutral point. So you may have a high pH. If you are talking about the CM, like sulfonic acid group containing membrane, then the pH of the membrane might be different, lower. So by using the indicator, if you have a small amount of indicator solution, put it on top of it, the membrane, then color will be changing if it has any cations on the surface of this membrane. If the membrane has anions, then it will be changing color. So by knowing this way, I think we can qualitatively at least indicate that this membrane may have a charge. Okay? So this is the qualitative determination of the electrical charge. But we can determine the permeability, of course, hydraulic permeability of the membrane, so that the membrane may have filtration capability. What about the defects or pinholes? Well, if you look at the surface of this stained means that if you have any color changes, colors such as yellow color or the blue color spread on top of your membrane, you may find some defects, some pinholes, if there is no color changes. For example, if you have small white spots or small white non-color changed spots, that means that we may have lower, or we may have the membrane without any charges. But if there is any pinholes, then there will be no charge, so that we can easily see the effects or pinholes. So those spots, if there is any spot, then we can see that there will be pinholes. If you take a look at the membrane and the light transmission will tell you about the presence of your pinholes, of course. So that's another way of indicating that the membrane may have pinholes. Long-term stability of particularly the chemicals. Well, your membrane may be put into the oxidizing agent. We call it as the Phantom's agent containing ferrous oxide, and put it immerse that membrane in the solution, and take a look at also observe the outer surface of the membrane, where the membrane is dissolved, and the dissolution time is your indication of your stability. If you have a long time of your dissolution time, it means that this membrane has a high chemical stability to these phantom solutions. Whereas if you have a smaller or a shorter time for degradation, then this membrane is quite easy to be broken, to be oxidized in the solution. So Phantom's agent will be quite useful to determine this long-term stability of the chemicals. We can check the ion exchange capability by knowing the ion exchange capacity or resistance, particularly to the electrical resistance, and the selectivity. Selectivity means that if the membrane has both of those charges in the field, and membrane may have one of those charges, what about the selectivity? What about the selecting the membrane among the two charges? That's what we call the pump selectivity. And permeation of the counter ions, that's another way of making the proper determination. And water transport as well. So we will talk one by one. So IEC, so-called IEC, can be determined by the titration method. If you have a negative charge in the membrane, then you may use a positively charged alkaline solution. If you have a positively charged cation in the membrane, then you use the anion charged one, such as a proton, the HCl. So if you have a cation exchange membrane containing anion, then you use the proton as a dropping agent. Whereas if you have a cation, such as high pH groups like ammonium groups, then you use the negatively charged hydroxide as determining the IEC. So you equilibrate with the certain concentration of this acid or alkaline solution, and put the membrane inside of the solution and rinse them later, and you determine by the titration of the other the acid or the sodium hydroxide, and look at how much the solution was consumed, and then you can back calculate what about the charge, how many moles of the charges that you have is what we call the ion exchange capacity. Weak-based membrane can be equilibrated using this the silver nitrate as well. So by using this membrane, we can determine the IEC, and the next step that we will do is another parameter in the electrodialysis, such as the electrical resistance. Well, we need to know about the units, such as watts centimeter, watt meter, watt square centimeter, watt square meter, stuff like that. And this will be these two terms, like the square, is much more useful in engineering point of view, whereas watt meter or watt centimeter is good for the academic point of view. So elliptical resistance of the membrane is determined by the IEC and the mobility of the ions. So IEC is one of the basic properties that you have to measure, and you need to know about the mobility of the ions within the polymeric matrix, membrane matrices. In this case, we are using the area resistance. In both cases, if you're using direct current, or alternating current. If you're using DC or AC, so by applying those two currents, you need to measure the area resistance of the membrane as well. So we need to know electrical resistance, area resistance, and IEC and the mobility to determine any of those electrical properties of the membranes containing the ions. First thing that you will do to determine this resistance is that in this case we are using direct contact DC. So we put the membrane here. So we have usually in this case we use one normal KCl solution as an electrolyte. And in this case, we have two chamber, and we put the electrodes of each side, and membrane is placed in between these two chambers. Now, there are two capillaries coming from the two chamber, and why we have two chamber is that if we do not have any electrical current between the two chamber, between the two membranes, well, then we can say about the osmosis. But if we have electrical current from each side, like the anode side and the cathode side, then we have electrical distribution of the charges across this membrane as well. So we have a capillary, and we have a tester solution, and we put the another membrane, of course, here, and from this anode side, if there is any the electrical current is applied, then you generate the gas like oxygen. On the opposite side, you generate the solution hydrogen as well in this case. Now, in the case of tester solution, we usually use this sodium sulfate solution, 0.5 molar or 1 molar. So tester solution is a sodium sulfate in this case. So through this membrane, if you apply the current, then negatively charged membrane will be transferred here in this case, and coming to the anode side because you apply the current. Whereas if there is any positively charged ions in the solution, then it will be collected into the cathode side. So this way, you can have the flow of the ions in using this ion exchange membrane. If there is no charge, then there is no flow across the membrane. Okay. So this is the and if you have a voltmeter here on both of those two sides, then you can obtain the voltage drop or the potential drop across the membrane because of the exchange of the ions in this case. So if we summarize what we have done, that in this case, the potential drop between the capillaries, the small capillaries, along the line of the membrane, is measured with the membrane or without the membrane. Okay, without the membrane, then the solution, the electrical potential or potential drop will be used as a calibration curve. So you have to deduct the effect of the solution when you want to know about the pressure drop due to the membrane, due to the presence of the membrane. So pressure drop using the voltmeter is measured with the membrane or without the membrane in the test cell, and you can change your current density passing through the cell, of course. We have a resistance here. We have the resistance. We have the area resistance, and we have the membrane resistance. So the resistance is given by the slope of the current versus the voltage drop curve. Well, resistance is always given by the current and the voltage, which is plotted here in the next slide. So we have the current density and the voltage here, and so usually you have some type of linear plot. If you apply the higher current, then you obtain the higher voltage. So the slope here is called the if you only have a solution, then you obtain this plot in the lower part. Okay, so the solution resistance is obtained by the slope of this curve. Whereas with the membrane, you have a high voltage, so that the resistance is much higher than the solution itself. So from this plot, we can say that the resistance of the total membrane with a solution, membrane and the solution, which is called the area solution, is the resistance of the membrane and the solution times the AN, which is the area of the membrane itself. This is the voltage divided by the current density in this case. The membrane resistance, therefore, membrane resistance is Rn, and we measure the Rn plus S, and so that the Rn plus S is the Rn plus Rs, of course. Rn is the resistance due to the membrane. This Rs is the resistance due to the solution itself. So the slope that we measured here is in Rs. This is Rn plus S. So Rn could be determined by these two slopes. So the first step to measure this resistance of the membrane is using this, the caramel electrodes to measure the voltage versus the current. And area resistance, if you plot the slope here, at each point, then it will be almost constant, as you can see here. Anyway, this is the easiest way of measuring the resistance, the area resistance, the membrane resistance. If you are under the direct current, but if you have an alternating current, then you have to correct some portions. Resistance measurement with and without the membrane can be performed in the cell, of course. And I think there are some error here. The specific resistance P, I think it's a P or rho here. It's the same thing. And all of those P are rho in this case. Anyway, if you have a membrane. If you have a membrane, here, and put the solution, electrolyte solution in each chamber, and apply the current in the alternating current. You can measure in the similar way. You can measure the area resistance and membrane resistance in this case. The area resistance is related with the specific resistance. This Rm is the area resistance of the membrane, and rho ms and rho s are the specific resistance of the cell with the membrane and without the membrane. So if you know the specific resistance, just like what we have done in our case, using the direct current, we can measure this rho s and rho ms, which is the specific resistance. And by knowing the d, which is the thickness of the membrane and the cell, and distance between the electrodes, which is electrode between the electrodes, then we will be able to calculate the area of resistance, Rm, here in this case. And by knowing the distance and the area, we can calculate the total specific resistance here in this case. So by knowing the specific resistance of the solution, specific resistance of the membrane plus solution, we can calculate the area of resistance Rn by using this alternating current in this case. So this is the principle of how we can calculate the area of resistance or membrane resistance by using the alternating current. And that principle can be applied to measuring the impedance spectroscopy. Impedance is the one related with the resistance, so that we can calculate, we can measure this resistance or impedance by using what we call impedance spectroscopy. Frequency of the alternating current can be changed, okay, and can be responded to the changing the frequency, and this is how we can measure the impedance in this spectroscopy. So potential of the solution, potential of the membrane, and potential of the electrodes can be described elliptically by the equivalent circle in this case. So if there is any spring, which is if you have a membrane here, membrane may have resistance, membrane may have a conductance. In the case of solution, we have some resistance. So the resistance model is described here in this case in using both RS, RM, and CM. CM is the conductance of the membrane. RM is the resistance of the membrane. So we have a parallel model and series model combined together to describe the whole system of impedance spectroscopy in this case. So as we have already seen in the previous slide, we have an electrolyte solution. We have a membrane, which contains some ions, which contains some, of course, ions. And we have electrodes, reference electrodes. And this electrodes is applied, connected to the impedance spectroscopy, spectrometer. And this whole system is what we call the impedance spectroscopy. So by changing the alternating current, we will be able to get some response from these two spectroscopy. Describing the principle of alternating current, the impedance spectroscopy is a little complicated. We have Z, which is the same as R resistance in the direct current. Z is a resistance or impedance. Now we have a small character which is omega. Omega is a frequency. So if you change your frequency, then resistance will change. So this resistance depends upon your frequency of the alternating current. And U is again the voltage, and I is the current, and so that the resistance or impedance is a function of the voltage divided by the current. And U and I are expressed by the those sinusoidal curve or cosine curve. Here, the omega again is a frequency, and phi here in this case is what? Is an angle between the because we are talking about the frequency, we have some lag of the distance between the sine of the curve and the frequencies, so that you have a little bit of an angle between these two. And T is the time, so that the voltage can be described here. Voltage and the current can be described here in this case. And impedance then can be if you put this 2 into here, you can describe and rearrange this into 2 parts. And as you can see here, we have a real part and the imaginary part because we have I here. And so in the alternating current system, impedance can be described by the 2 systems, real part system and the imaginary part systems. Real part system is equal to the what we call the resistance in the direct current system, whereas the imaginary part is related with the capacitance. So when we are talking about the only the real part, the imaginary part is zero. We are talking only about the imaginary part and the real part, where resistance is zero, so we are only talking about the capacitance. So capacitance is the main part of the imaginary part here. So capacitor is known to the system where you have a phase shift between the current and the voltage with the phase angle of the phi 2. So the impedance of the capacitance is frequency dependent and is the imaginary part. So we wanted to know about the information about this imaginary part and the real part by using the impedance spectroscopy. And the information that we get is that we have impedance in the real part, which is in the x-axis. In the y-axis, we have imaginary part. So this in these 2 axes, the G real is what we call the resistance. So magnitude of where we are going is the resistance. It could be plotted like here, and each of these curves depend upon the angle of your phase changes. Okay, angle. The frequency of where we are going. So if you have a high frequency or a low frequency, then you have a high imaginary part or a high low imaginary part. That is what we call this phase. So if you plot the impedance with the frequency, then we can obtain some of these functions. So it's a little what we call the Arganda diagram, and the Bode diagram. It can be both effective in the impedance spectroscopy. So total impedance, overall impedance can be described that we have a real part, which is the resistance, and the capacitance. Both of these two contribute to the total impedance of what we measure from the impedance spectroscopy. So imaginary part will disappear at very high frequency region, because if you have a high frequency, then the denominator will be infinite. So total sum will be generated. So high frequency region impedance is identical to the ohmic resistance here. But at low frequency region, this capacitance will increase, will decrease in frequency, and will be infinite in this case. So for total resistance and capacitance, the relationship will be following like this in this case. So it's a little bit complicated measurement, but we can have a very nice correlation here in this case. So in summary, we have a real part and the imaginary part, and these curves will depend upon the frequency and the total, depth of the y and x-axis will be the resistance, and this the frequency will be dependent upon resistance and capacitance. So this is the plot that we have, Argon plot and the total plot. So membrane resistance. Excuse me. So this part can be explained that so when we have a series model like a resistance, and capacitance, the total impedance can be described in the equation given above, whereas if you have a parallel model, the equation on the bottom can be effective in this case. So depending on the systems, you will be able to describe these two equations. So in summary, impedance spectroscopy will give us information about the difference in the impedance with the membrane and without the membrane, so that you can calculate the membrane resistance here in this case. Because we are using the alternating current, specific resistance of the membrane is the same order of magnitude with that of the electrolyte solution. In order to obtain more reliable data, we once measured the resistance of the membrane, but if you have many of those membranes in series, what we call is a stack. This is what we call the stack. So if you measure the resistance of the total stack and divide that with the number of membranes, then you can calculate the membrane resistance of the total systems. So this is more a precise way of measuring the impedance in this case. So we recommend to measure the resistance using the stack in this case. Okay. So there might be some error in the membrane resistance measurement and impedance spectroscopy measurement because of the membrane geometry, membrane surface roughness may give you the different results. If you are using the commercial membrane, I think that the error between the measurement of each different membrane will be quite minimal. But if you are using the membrane cast from your own laboratory, then membrane to membrane deviation might be quite high. So the surface roughness of each membrane will provide some errors into the measurement of the impedance. So you have to be very careful in the case. Anyway, to determine this problem, to avoid any problems related to this determining the membrane resistance, the contact point between the membranes and the electrodes are very important in this case. So in some impedance spectroscopy, electrode is applied on top of the membrane. So right on top of the membrane, the electrode is attached here in this case. So you supply the electrolyte solution here, and if you put the membrane and put the contact membrane, which is sort of a reference membrane, you can minimize the error between the working electrode and the test membrane. So in this way, you can protect any error generation in this case. The second, the very important aspect, other than the IEC and the resistance, is the pump selectivity. Pump selectivity. Because we are talking about the cation exchange membrane or anion exchange membrane, or maybe bipolar membrane. Bipolar membrane is the one that contains both of these two charges. If you're talking about cation exchange membrane, you have fixed ions. Okay? Cation exchange membrane have an ion, such as a sulfate ion, in the membrane. And if you have both positively charged ion and anion from the solution will be expelled, whereas a cation could be attached to the cation exchange membrane. So cation will be exchanged anyway. If there is the exchange of the anion coming through the membrane, your selectivity is now 100%. Okay? If your membrane will pass of both of those two ions, then the selectivity is 0. So pump selectivity will determine, how your membrane will be transporting the selective to each of those the ions. Is what we call the pump selectivity. So cation exchange membrane should have 100% cation transfer, whereas anion exchange membrane should have 100% anion transfer through the anion exchange membrane. If your pump selectivity is 98%, then 2% of the counter ion will be, of course. So pump selectivity is determined by the ratio of this specific component to the total flux. So you measure the flux of cation transfer and the anion transfer divided by the total mass flux is your pump selectivity. So you have to measure the transportive ions through the membrane to determine the pump selectivity. So in the case of pump selectivity, we need to know about the parameters, such as pump selectivity here. Pump selectivity is a function of transfer number of the cation and counter ions. So you have the CO and the COU. COU is a counter ion, CO is a cation, and T is a transfer number. How mobile how fast your ion will be transferred. Counter ion or the cation will be transferred through the membrane. There's a TCOU or a TCO, and M represents a membrane. So the pump selectivity is determined by the TCOUM minus TCO divided by TCO. Now TI, transfer number, is defined as the Zi and Ji. Ji is the flux of your ions, whereas jet is the valence. Valence means if you have monovalent or bivalent or stuff like that. So Zi And Ti is transport number of I component through the membrane. So if you have a flux of each, how many ions that you have, the total molar flux is in the denominator. In the numerator, you have each of specific I component flux with the valence is what you can call the transport number of I component. So using this flux equation, we can determine the pump selectivity of each element. Pump selectivity can be determined by dynamic way or the static way. Dynamic way or static method is the same as what you can imagine. The static method is the measurement of the potential gradient across the membrane in the closed chamber, so you have a static rates. Whereas dynamic method is the one that you have a counterflow, so the concentration of each will be determined. So this is the true membrane resistance or pump selectivity, whereas the static method may have a following effect. So this is what they call the apparent the pump selectivity. Pump selectivity is related with the Donan exclusion principle. Donan exclusion principle is the one that if you have a counter ion, then you have attraction. Whereas if you have both of the same ion, you have exclusion, repulsion. So Donan exclusion principle is applied in this case, and the membrane potential is the one that you have Donan potential between the membrane and the adjacent solution. So you have a small layer, the boundary layer, resistances and so on in this case. So the potential of the membrane through the membrane is related with the Donan potential of the first component and the second component, whereas you have diffusion of the ions, in this case for this Donan potential contribution. If there is any Donan exclusion principle, then it will be eliminated. So the total membrane potential is the same as the potential only contributed due to the diffusion itself. So we knew that we can determine the pump selectivity in many ways, and we can describe this the Donan exclusion principle and the other the boundary conditions and so on, and you can derive the same some other very complex equations, which is out of the scope of this characterization method. I hope that you can look in more detail about what's going on if you have different complex systems. Transport number. So we have talked about the transport number, the phi m, because phi m, membrane potential, is related with the transport number of counter ion and the co-ions. And if you have a specific membrane resistance potential resistance, we can describe this equation here. We can rearrange this equation by knowing here. And anyway, there are some relationship between the membrane potential and imaginary part and the real part is opening in this case. So by adding a small amount of the salt in the solution, we will be able to determine the different transport numbers in this case. So in many cases, the membrane potential or membrane impedance is described as the potential of the membrane, the real part, and the specific part of the cases. Well, this is the same as what we have described already. We have two, the membrane is separated with two solutions, and you have a small concentration and the high concentration solution. And if you put the caramel electrode and put the voltage, and if you apply the current, then you may have transport of the ions because of the concentration difference. The membrane may have the ion may have a transport through the membrane if you have electrical tension. So membrane we can determine the selectivity of the ions and counter ion or coions, depending on the systems, depending on the systems that we're talking about. We will. Next step is the one that we will talk about the osmosis, electroosmosis. The difference between the osmosis and the electroosmosis is that we have ion exchange membrane in the case of electroosmosis, whereas in the case of osmosis, we may have a different membrane without any charges. The concentration difference or activity difference between the two solutions across the membrane or in the two chamber will give you a osmosis because you have osmotic pressure difference between the two solutions. Whereas in the case of electroosmosis, you may have some charges in the membrane. And you have to apply the current in the two chambers. The difference between these two systems. So we will talk about the osmosis and the electroosmosis. So osmosis is a result of a concentration difference between the two solutions. Okay. Whereas electroosmosis is the one that your water is transported by the ion migration through the membrane. So this is the system for osmosis. If you have a membrane, okay, and in one chamber we have a sodium chloride solution, and in the second chamber we have only water. We have a high concentration water and low concentration water here. So activity is high here to low. So the water transport across the membrane because of the osmotic pressure difference. This is what we call the osmosis. But if you apply the pressure, from the left-hand side, higher than osmotic pressure of the system, then water will be going from left to right. This is what we call reverse osmosis. So osmosis is the one that you have water transport from the high concentration water to the low concentration. Whereas the reverse osmosis is the one that your water will be flowing from low water concentration to high water concentration. But you have to apply the pressure higher than osmotic pressure of the first systems. Whereas, so water transport here in this case, if you have ion exchange membrane, so let's we have a water, sodium chloride solution here. We have water here, or we have sodium chloride in each case, and we put the ion exchange membrane and apply the electrode, just like what we have described earlier. And water is transported, of course, and the sodium ion will be transported as well. So because I think this is the same as what we have described in the electrolyte solutions. So water transport due to the electroosmotic pressure is due to the transport number in this case, just like what we have done. JW is the water transport across the membrane, and I think this is the current density, and F is the Faraday constant. So by knowing this flux of water, then we can calculate the transport number of the water through the membrane. So in this measurement, usually the direct current is easy because you are not influenced by the frequency aspect. So the direct current is applied in the case of this measurement. And both compartments of the test cells are filled with the test solution. Usually this is the sodium sulfate solution. And the example is that this Na plus sodium ion transfer across the membrane. So this is what we call the cation exchange reactor. And it contains negatively charged ion, of course. So by measuring the volume change in the two compartments, we will be able to determine the movement of the ions through these two channels. Volume of the cell change due to the electrode reactions. The electrons or the ions will be generated here in each electrodes, so that there will be a flow of electrons which will generate the electricity. So by using this principle, we can generate the electricity as well. The volume change of the flow system can be described here in this case. And so the total volume change and the volume change due to the electroosmosis of the cell can be determined from this equation. The total the volume change is due to the flux the water transport number through the membrane, and the VW, which is the partial volume of the water in this case. So if you're using the different cations, you have a different electroosmotic water flux. So water flux is dependent upon the type of the cations that you use. If you have a sodium chloride, or if you have a calcium chloride, or whatever, you have a different transport number. So far, I think we have talked about the electrical property and the electroosmotic property of the membrane, and impedance spectroscopy, the importance of the transport number, and so on, if you're dealing with the ion exchange membranes. For the last two slides, we can talk about the specific property of the membranes. In industry, they use electrodialyzer to concentrate to make the sodium chloride or salt from the seawater. That's what we call the electrodialysis using the ion exchange membrane. In that case, specific property measurement is required. As you can see here, concentrated seawater or pre-concentrated seawater is used to make the table salt. Now, there are many types of salts, in fact. We use only, in Korea, we use only white salt, right, from the seawater. But there are many types of salt, which might be very expensive. In the other part of the world, you use different type of salts. It is in some cases it's much tasty salty or less salty depending on the crystal types. Anyway, we are making the crystals, particularly sodium chloride crystals, using what we call the membrane crystallizer. And what it is that you have concentrated, pre-concentrated solution in the feed, and if you drag the water through this membrane, then the feed will be much more concentrated, and it starts to aggregate on the surface of the membrane, and could be grow on the surface of the membrane because you already formed the nuclei. So crystal formation is observable in many cases. So depending on the type of the surface that you're talking about, you have different type of salts, different crystals. It could be monoclinic or orthorhombic, depending on the crystal formation. So it's quite interesting, and even in the restaurant, they provide different salts with different taste. It's interesting, and in Korea it's not very popular, but in the other parts I think it's very popular. And you can, of course, make the different salts from different nuclei, from forming agents. Anyway, in order to pre-concentrate the seawater, we need some membrane with low permeability for diluted ammoniums in some cases. In the case of bipolar membrane application, bipolar membrane is the one that you have both of those two charges in the membrane. Usually the acid group or basic group is present in this case. Then you have you have to measure the different properties in this case. So I don't think this is the topic that we will cover at this time, but I think you can, in order to have a specific property of the electrolyte membrane, you have to look for specific applications. For example, if you are using the bipolar membrane, you need to know about the electrical resistance, of course, and the pump selectivity. But you need to know about the water dissociation curves or the water transport limitation curves, just like what we can see here. So current density versus the voltage drop was linear in our case, in the case of basic solutions. But in this case, this is not linear. You have some regions. There is a transport of the salt volumes, whereas you have a dissociation of the water, and the transport limitation is determined in this case. So, for specific membrane application, you will need to know the specific property of the membrane if you go more deeply into the ion changes membranes. Okay. So this is all that I can say in terms of the membrane characterization. And next topic will be about the special topic, and I think we will, I will provide some PDF file beforehand, at least before the weekend. Before the end of the weekend, so that you can read and come to the class in Wednesday. we don't have a class on Friday. On Friday, I will give you the take-home exam. And you can return to that answer directly to me. So next week will be the final week that I can teach the class, whereas the week after next week, Professor Gioli will be coming and teach and continue this discussion along with guest faculties like Professor Don Paul and Dr. Elena Tuch that I mentioned to you at the beginning of the class. Any questions, comments? So I'll give you the program set of the take-home exam next Wednesday. What I'm going to do is that I will give you a couple of review papers, okay, and so that you read those papers and answer to my questions. So I'll give you the program set and the papers, okay? Okay, with that, thank you, and I will see you on Wednesday.